Ready? Okay, here we go. Structures. Your machine is nothing without a structure. You're nothing without a structure. Watch what happens when I take the bones out of my body. Okay, so no matter what kind of a machine you've got, it'll have actuators, sensors, it may have any of that, you may or may not, but you will have a structure or you don't have a machine, you have a jellyfish. The way you design a structure for your machine is, again, you follow the design process by figuring out, okay, here's the function that the machine has to accomplish, and systematically going from coarse to fine. The coarsest form is creating this virtual volume into which your machine must fit, and then filling into the machine, starting at the very beginning, fundamental principles, remembering your materials, all the way through this design process that we will talk about in topic 8 now. So diving right in, once again, history is very important. One of the key people in structural design is Stephen Timoshenko, really interesting cat who also wrote this really neat book, History of Strength and Materials. Highly advise reading this. Going back in time, remember Saint Venant and Saint Venant's principle? Leonard Euler, due to figure out how beams bend. If you give a mouse a cookie, when you start designing a structure, it's very, very easy to start piling on complexity. So always take a deep breath, and we're going to start simple. We're going to remember our history, what kind of structures out there exist, for example, truss structures, and how can we build upon what's out there to lay out the simplest possible framework to support the machine that we can. So we'll start with the fundamental principles, and the most important is the structural loop. When you have a machine that's been given to you to design, remember you'll have some tool that'll operate on some workpiece, and you're going to be given a range of motions that the tool must do with respect to the workpiece, and now your responsibility is to figure out the rest of the machine. And over that range of motion, remember we're going to have the structural loop. And we talked about in topic 3 the ways to draw the structural loop and what it is, so go back and review them. What I like to do when I'm designing a machine is literally I have the tool, the workpiece, and I'll start writing down my requirements for the types of motion. And often this will come from your concepting of the machine itself in terms of am I going to have linear or rotary motions and what combination. I can have all linear or all rotary or some combination. Remember from topic 4, rotary, multiple rotary at the same point would give you spherical ultimately. And my goal is to start envisioning different types of structural loops to accomplish this relative motion between the tool and the workpiece that are combinations of the linear and rotary axes, drawing the structural loops that I would achieve with the different combinations of axes in order to accomplish the function of the machine. Those are very fast, simple words, but really, really, really deep. Because remember from your knowledge of a structural loop, as the machine moves, you would like the shape of the structural loop to remain as constant as possible. You would like the length of the structural loop to be as small as possible. The smaller the structural loop is, the greater the potential stiffness of the machine. Remembering the lesson from a normal just cantilever beam of length L, that the deflection goes like FL cubed over 3EI. So the structural loop length typically has a cubic effect on the stiffness of the machine. So having a great big machine to accommodate any size part when you're mostly operating in little itty bitty parts may start to tell you that the cost of that machine is going to go way up in order to give you the stiffness you want for operating in the small zone, and you may be far better off on having a family of machines that will handle from small to medium parts, and then from medium to large parts, and then large parts as opposed to one machine that you're going to use for everything. Okay, so that's another key point. This is not only true when you're designing machines, but when you're buying machines to accomplish a function, what you may expect to pay. Very, very, very careful in terms of thinking about how much stiffness you need. Go read Aesop's fable, The Oak Tree and the Reed. Very, very important in terms of thinking about, do I want infinite cosmic stiffness? Or is it better to bend with the forces and accommodate them with your control system or other strategies in order to minimize cost and maximize survivability, flexibility? Now, when we look at some of these different machine tools, you'll notice you have open structural loops, closed structural loops, different machines accomplishing different functions in terms of the stiffness you get and the operating environment the ergonomics of operating with the machine. Now, having thought about the structural loop, now let's think about what are the materials that we would be using to accomplish that structural loop. Sheet metal, tubular, extrusions. How does a spider build a web which is very flexible yet very strong? How do you take soft materials and accomplish softness in a structure, rolling diaphragms? A very, very important part of this is going to be the tactile. How does this feel? How would I use this in a structure? Individually, these wires would be very soft, but when you weld them together to form a truss, very stiff. Yet I can actually torque it okay. Why is this beam designed as it is? See, it looks like an I-beam, yet it's tapered. And what do these holes do? Do they just reduce the weight? And is it really worth it to bore out these holes for the weight savings that I get? This looks like a beam made out of Legos, yet it's fairly flexible. Yet close up, it's pretty stiff. See, when it's long, though, is when it gets more compliant. And watch what happens now also. It's actually pretty stiff given it's Legos. But see how soft it is in this direction? We're going to talk about the torsional ability of structures. And because it's soft in torsion, remember, torsion is force times distance. What happens when this beam is loaded symmetrically, but if I load it off-center, watch what happens. See how it twists? A very common failure mode in a structure is if you take a beam and it's not loaded through what's called the shear center of the beam, you'll get a torsion which can then cause it to buckle and fail. So you have to be very, very careful how you actually load beams to ensure that they don't have one of these torsional instabilities in bending. So make sure you really go back and learn your mechanics of materials very well. As a design person in a design class, understanding the mechanics of materials is absolutely critical to building the structure. And feeling and touching materials is a good way to preload your brain with the feeling of what the materials will do under load. You become one with the materials. You can feel the forces going within them and how they will move. And that's actually really important. You want to be able to see the motion of the structure, play the video in your head, envision what happens. And then when you are sitting down at your CAD station and you're designing things and you're doing your first order calculations, you're doing your finite element analysis and you get the pretty colored pictures as to what the motions are, that will only seek to verify and strengthen your ability to visualize what a structure is doing, which will enable you in the next time you do this to do it faster. Now, here's a little exercise I want you all to think about. See this little space alien dude? Notice the symmetry. And here's a square hole and this barbed shape. How does that go in? It doesn't. But I can mush it and force it through with that tab. Okay? How would I take these things and make a tetrahedron. See, I've got soft materials here, and they're all floppily. And watch what happens. I can actually make a four-sided structure from 3 of these. So this is one of those little mind game puzzles. And if you ever like to play with or do puzzles, make sure you go ahead and play with puzzles so your fingers feel how things go together. It's an incredibly valuable way of teaching your brain to visualize structures. Okay? And when you do that, and you start to preload your brain with how things fit together and how they feel, you'll be able to think better when you're faced with the task of designing a machine and trying to figure out how all the complex pieces are put together, and to minimize things and to use your materials wisely. So, like I said, I can't emphasize enough the power of physically touching and playing with things to solve puzzles, to reinforce the ability of you to close your eyes and think in the abstract and come up with designs. Okay, there you go. It's a 3-sided tetrahedron, and tetrahedrons have 4 sides, right? So it's a pyramid with 3 sides, even though pyramids have 4. Okay, so remember, materials can let you do fun things. Now, whenever I pick a material and I'm using it in a structure, think about where, if the materials have to move over each other, will they abrade with time? What's the static strength of the material? And what's the inherent stiffness, which really is a function of the modulus of elasticity of the material? Also, when you have a high-strength steel, it comes along and the linear regime starts to yield and then, bang, breaks, versus a much more ductile material, which may be softer in terms of lower modulus, like aluminum, and it really just kind of oozes before it breaks. Also remember that all ferrous alloys, essentially all steels, will have the same modulus of elasticity. They may have a different ductility before they break, but this slope in the elastic region will always be the same, within a percent or a fraction. You may have a small variation due to rolling direction, some heat treat effects, but for all intents and purposes, it's the same. So the modulus elasticity of all steels is the same. The modulus elasticity of all aluminums are the same. Small variations for rolling direction, heat treatment, but never assume that I can make a material stiffer by heat treating, for example. No, it doesn't work. You have to physically change the type of material. So getting back to visualization, look at structures around you and how they achieve the stiffness. Look at bicycles. Look at, for example, the bicycle brake mechanism, the detail around the derailleur. Look at it, and I like bicycles because you actually ride bikes and are familiar with them. Look at it, and then put it up on a bike stand and shift the gears and apply the torque to it, and look and see how the system is deforming. I don't advise you to be watching your bike while you're riding it, to watch, oh, really torquing hard, oh, wow, well, look at that deformation, bang! Because then you may deform yourself as you smash into something. So don't do the experiment while actually riding the bike. Now, take a car. When all the doors and everything's closed, it looks like a solid structure. Whoa. But then open up the doors and everything. Open it all up. And how can this thing be stiff enough to drive? How can it be strong enough to absorb an impact if you are unlucky enough to be in an accident? When the structure is open, what's the performance? When it's closed, what is the performance? So you can also start thinking about your machine in configuration 1. When you're doing maintenance or something on it, it's wide open. And then when it's closed, the panels become part of the structure itself. And this is a very, very important attribute of a machine if it can be low cost, very open and accessible for maintenance, ergonomics, loading. And then when it's in the operating position, things lock together to become very strong. For example, my little foam rubber doohickey here is much stiffer when all the pieces are locked together than the individual pieces of foam. Okay, so that was a very important lesson that we came to. The structure can be self-reinforcing when in the engaged position. So remember back to topic 3, the concept of self-help. When you look at, for example, when they're putting up a building in the steel structure, you wonder sometimes how this wobbly frame is going to survive an earthquake. And then if you look carefully when they're putting up steel structure, you'll see often selected diagonals through the building. And it just takes a few diagonals to stiffen the whole building up. You also may wonder sometimes, how do they build these giant tall buildings? And you go up to the side and you look at, wow, it's perfectly straight. How do they do that? Put everything together, and where along your structure are the sensitive directions that if I apply loads along a diagonal, for example, I can do a slight load and then make it stand tall. So remember, structures, when you're visualizing how they perform in terms of handling the primary loads, start to think about what are the sensitive directions in the structure. Remember sensitive directions from topic 3. Which are the directions that if I apply a force, I can use to pull the structure to be square or the shape I want? Which of those directions also I have to be very careful of in operation? If a force is applied to the structure, it'll cause a large unwanted deformation. Notice that's the application of the principle of reciprocity. 1 over ouch equals ah. But you got to be careful that you don't get ouched when you think you're eyeing. So having loaded these concepts of the structural loop, thinking about materials, strength and stiffness, let's now talk in a little more detail about layout. And I want you to absorb everything in your head that we've been talking about up to date, coming back to our design for our new type of table. And let's start talking about how would we lay out the structure of the new table design for the drill press so we can actually start getting into the detailed design phase. Okay, you may recall previously there were several options for this new table design we were looking at. One was a purely rectilinear motion of X and Y, and the other one was rotary motion joints. And for simplicity here, I'm going to focus just on how would I do this table such that to position the part, I'm not depending on this rotary motion, but I'm just getting X and Y, kind of like a milling machine. And how would I actually do the layout? Well, I'm going to keep in mind my functional requirements are going to be, I need to be able to position my part in a plane. And I'll be happy with just X comma Y in terms of just, I'm going to go this way and this way. I'm not going to worry about I have to orient the part because I'm drilling a hole. So rotary orientation doesn't matter. And I want to create a layout drawing. And the layout drawing is going to be the first embodiment of the design intent. It will define the boundaries on my structure. I'm going to start with stick figure sketches, and I'm going to get into more and more detail. And to think about the layout drawing is the graphical intent of the function requirements, the design parameters. Here I'm going to want to have X motion and Y motion. I'm going to define the size of these later with my analysis. And that's going to be used for my stiffness, which will affect when I'm putting loads from the drill on it. I don't want this thing to sag such that the hole goes through the part at an angle. And the strength, because I don't want to have someone come along and push so hard on it it breaks. And of course, I've got references. There are X, Y tables all over the place. risks and countermeasures. Okay. So I'm going to start by doing my layout by here is the vertical post. I'm going to assume that's a given. So this is a plan view looking down. Here is the tool. And I'm going to want to have this be my work zone. And I have to be able to define how much the part should be able to move up and down and left to right. So if the part is half as big as the distance from the tool or the center line of the spindle to the column, then one would expect that this is the part. I can move this so that this tool can drill on this edge or this edge. So nominally we're going to say that the maximum width of the part is the distance from the center of the tool to the column, which would then also define now the range of travel of my stage in the, we're going to call this the y direction. The x direction is much more wide open into how far we can move. Now it becomes the question of how far do you want to move without having to clamp and unclamp or refixture your part. If you made it really big, well, you might as well have a milling machine. So we start thinking, probably seems reasonable that the x direction motion, to start anyway, is on the order of the y direction. Okay? We're going to have to be very careful that we're going to not jump right into a solid model as a layout, and I'll be doing solid modeling later on as a separate module to go with the class. For now, we can be very good at just sketching things out by hand. Okay? So how would I sketch this? You see here, there's some sketches that have, if we start with this, with the coarse ranges of motion, just arrows and stick figures that will then get to higher and higher level of detail before we ultimately end up with a solid model. Okay, so you think of the design like a flexible anagram. You're allowed to only rearrange certain things. You can add or subtract things. You can use different colors to have different mechanism. That's why sketching in your notebook with different colored pens is very, very powerful. Before I come back to this sketch, remember you have to keep in mind as you start to think about great ideas what you're trying to accomplish, the functional requirements. Here, we said here, we want to position our part in x, y, and then we're going to start sketching mechanism. So let me go back to sketches, and let me get rid of this. We have a little more operating room. But we're going to keep those Fred part parameters in our head. And now I'm going to evolve this design into starting to lay things out. So the first thing I acknowledge to myself is I'm going to start vertical. And here's where the tool is. And this is the range of motion I want to accomplish. So I'm going to make this a table. This is what my part will lay on. Let me switch colors here. And I'm going to draw it in this position neutral, and I'm also then going to draw it over shifted. And by doing that, I start to build in my head thinking about, and that's a later topic, so we'll do the details later on bearings, but this is what this table does. It normally starts here and it slides over, and then it changes the position to the other side. So I start to think, how can I accomplish that? Remember St. Vinay's principle. What does St. Vinay's principle tell us? Well, I need to have certain proportions, and if this table is L length, I know if I'm going to do linear motion, I'm going to have some bearing support, and I have two options. I can, one, fix, for example, the bearings on the table and have the rail fixed to the base so the table moves on the rail. If I were to do that, that would mean that, for example, I put a bearing block here and then a rail underneath it, where the rail is fixed to the column. St. Venez tells us if this is L, that this bearing engagement better be at least L over 3. If this table gets much bigger than the spacing on the bearing blocks, then it's going to be too soft. What else do we notice? Now we're playing the movie in our head. When we move the table, and let me actually just draw a different scene. Here's the column, and if I were to put the bearing rail here, and here's the bearing block, and here is the table that I moved in order to drill a hole here. So what am I going to say next? Remember, part of what you're doing is learning to anticipate. Strike before struck. What would be nicer? Move out of the way first. Watch what happens to the structural loop. Here come my forces for drilling. Drilling. The forces come through. It's like Alien. Remember that space creature? Icky. How do we keep a tighter structural loop? How do we keep a tighter structural loop as we're sketching out a design? The bearing block, the flow of forces, we want to always go from the tool into the part right back into the structure. Tight structural loop as opposed to this. So that tells me topologically in my brain, because I'm feeling the forces, that I'm going to keep the bearing block here, which means that a better design is to fix my bearing block and then have the rail for the bearing block on the table. See, this is the opposite of that, the reciprocal design. There are cases where this is better. You have more bearing blocks. It's a different design like a regular machine tool bed, but this is a drill press. It doesn't need the same stiffness and accuracy of a milling machine. If you needed the stiffness and accuracy of a milling machine in your drill press would become a milling machine. So right away you see, by thinking things through with these simple sketches, we're laying out what our machine will be, that this block will be attached to the column. So if I look at the side view, it's implying to me that here is this column where this goes up and down, and I have the bearing block, here's the bearing rail, and the table attached to it. So this moves in and out of the board. This is my x-axis. Now you're thinking, wait a second, but I need to move in and out in the y direction also. And if this column moves up and down, don't I get this rotational motion for free? So why am I having this rotational motion on the column and these x-y axes? It's a good question. But remember, if I'm trying to have a heavy part on here and I want to move it, I kind of can. This axis here resists me, this rack. It's kind of a mess to do that. And I have this rotational motion, which is really not any part of, if I have a part on here and I want to drill a series of holes in a line, this is bad. Okay, so we're going to say that the function of this axis is only to go up and down. Remember, I have to fix this gearbox. It's a clunky gearbox, but I can go down. I just can't go up very well. We'll fix that later. One day we'll take this apart on camera. So we're not going to mix the function of this axis moving up and down with the function of positioning. Okay, so the next step is we need to add the y-axis. Would it not make sense potentially? Is there some way that we can take this same logic and apply it to the in and out motion? How would we do that? How would we stack one axis on the other such that I can move this way and also this way and have the bearing block always under where the drill is going to be? How would we do that? Can we do that? Is it possible even? Okay, I'll let you guys figure that out. I did the first axis. You guys start to visualize how I would design the y-axis, the in and out one. Is it possible to get those two axes in one bearing block that allows the table to move an x and y very nicely? Can I buy bearings off the shelf that exist to do that? Do I have to invent some kind of a new configuration of bearings? How do you do that? Now, in the notes here, we have this example of for layout. And getting back to the peer review process we had also talked about way back in your youth. That was topic 1 and 2, on initially thinking of concepts. The different colors here and the different numbers represent the flow through of taking in ideas, different ideas, and having people comment on different layouts for designs. You similarly, as you've created your notebook with these ideas, want to pass it to a buddy, a peer, to review your ideas, comment on them, hand it back to you, or maybe have 2 or 3 people comment on your ideas. What I often do is, even if those people are not members of my design team, if I'm designing something by myself, I have a bunch of friends, and we all agree that we share things in terms of, you've got an idea, send it to me, I'll be happy to scribble on it, give you my thoughts, give it back to you. So we constantly are peer reviewing each other's thoughts and ideas, even though we're not all designing on the same team. It's really, really important to be able to have this impartial feedback from people to question you on 2 things. One, have you explained it carefully enough in your notebook? So you don't just have the sketches I drew here, you would have the sketches I drew here with annotations according to, for example, how I was talking through them. So someone can pick up your notebook and without talking to you, understand what you're doing and comment on it and give you suggestions for how to make things better. Okay? That's very, very important. If you can't convey your ideas with simple sketches and simple words for the sketches, you've got to ask the question, am I really conveying a well thought out idea yet? Okay, now what would be some of the next steps we would do after this? So here you see a water jet cutter, Abrasive Water Jet Machining Center. This company, Omax, makes these. I helped with the original design of these types of machines. And the key thing here in these machines was it started with a concept for, we want a very large open structure for a lot of easy user access. We want a very low-cost machine, yet it had to have a very strict set of tolerances in terms of the accuracy of motion. And there's no real load capacity on this machine because the abrasive water jet cutting process doesn't put a load on the part like a milling cutter. But under its own weight as it moves, it can't be deforming so much to cause unacceptable errors. A key thing is it's got to be low cost. So one of the topics we looked at was, how can we integrate the function of the bearing and the structure? And it went from some first order sketches, just like we did here, to some solid models and finite element analysis to look and see, could we use the bearing rail itself as the structure for a small machine? Can we take really giant, way oversized bearings and use the bearing block and the rail itself, and that's it? It turns out you actually can do that, and you can afford to do that, because some of these large bearings, this is a size 55 it's called for linear guide bearings, that we'll talk about it when we talk in topic 10 about linear bearings. This one here, by the way, I believe was a size, this is a size 35. So 55 is that much bigger. Turns out for this particular small machine, we chose not to do that. We used a different kind of bearing within extruded aluminum because it came out a little bit cheaper and allowed us a modularity that we liked. But for very small compact machines, this would be the way to do it. And the lesson here is went from concept sketch, first order analysis, solid model, finite element analysis to verify this type of joint structure, what the stiffness was, then a mock-up in the lab where we actually built one and did stiffness tests and dynamic tests to get our early results. Things actually worked out fine and actually very nicely for the machine's small machine size we're looking at. As we went up in size, things didn't work so well. Why? Because remember we talked about earlier, the stiffness is a function of the length cubed. And then one of the functional requirements is to hold the container of sand on the structure. That's the abrasive that's used in the water jet. And as this started to get a little bit longer, for the marketing said, well, we think we want this, quote, small machine to have a slightly bigger cousin. The size of this steel rail, see this solid steel rail, becomes just too big. It can't compete with having an aluminum tube with a smaller steel rail and bearing. This was just much stronger in the end than, and lower cost than just putting a bigger and bigger steel rail. The lesson, however, was not lost, that for smaller machines, you can often think about just using the rail itself as the axis. Okay? So remember, Fred Park, structure loop, the sketch, stick figure sketch, start to fill in the motions, do the reciprocal of what you think you want to check the opposite design. The sketch looks good with your first order calculation sizing, finite element analysis, build the bench level test, verify, then you can commit to a real solid model and start to do your production drawings. Now, talking about comparing designs. You can use design charts, you can use different finite element models to compare things, your first order spreadsheet calculations. Remember also, it's not just the analysis, but manufacturability and robustness. Look at your structure and what sorts of environment will it operate in. Is there corrosion effects? Bring in the manufacturing people also and ask them, how can I make things? Finally, you'll go from your layout sketch to your solid model. Now within a solid model, you'll have also the layout steps. You notice these bearings here. They're just drawn as squares. They're not drawn with all the detail of, like, for example, the bearing rail grooves. You don't need that. Similarly for gears, don't draw gear teeth. Just draw the gears of their outer diameter and then a dashed line for where the pitch circle is, where they'll engage. When I'm doing a solid model, take very, very careful, take great care to carefully draw it to be accurate in terms of the size constraints, but I don't worry about the fine detail yet with fillets and things that look good and that you need in the final accurate model, because the good chances are that you're going to change the design radically anyway. And if you put too much detail in your solid model, you get wed to it, and then you don't want to change anything. And you start making up design excuses. Well, this axis is really optimized. You know, oh my God, I don't want to change this thing. I spent a day putting the detail in. Oh, and he wants me to change it. Just because another design might be better. Oh, well, he doesn't really know that. Okay, so you should be free and easy with your solid modeling.